Hello everyone! Welcome back to our Finite Element Method lecture series. In the previous lecture, we learned about different types of finite elements, degrees of freedom, and mesh generation. We also understood that a finer mesh generally provides better accuracy, but requires more computational effort. Now, an important question arises. Do we need to refine the mesh everywhere? The answer is no. Instead of refining the entire model, engineers refine the mesh only where it is actually needed. This process is called mesh refinement. Mesh refinement is the process of replacing larger elements with smaller elements in regions where the solution changes rapidly. The objective is to improve accuracy while keeping the computational cost as low as possible. Let's first understand why mesh refinement is necessary. In many engineering structures, quantities such as stress, strain, displacement, or temperature do not change uniformly throughout the structure. Some regions experience very rapid changes, while other regions show only gradual variations. If we use a coarse mesh everywhere, these rapid changes may not be captured accurately, leading to incorrect engineering results. Therefore, we refine the mesh only in critical regions. Now, look at the example shown in the center of the poster. A plate with a circular hole subjected to tension. First, observe the coarse mesh. Notice that there are only a few large elements around the hole. Since the stress concentration near the hole is very high, this mesh cannot accurately represent the stress distribution. As a result, the solution has relatively low accuracy. Now, look at the second model. Instead of refining the entire plate, only the region near the hole has been divided into smaller elements. This refined mesh captures the stress variation much more accurately, while keeping the total number of elements reasonably low. Finally, observe the fine mesh covering the entire plate. This model gives the highest accuracy, but it also requires significantly more computational time and memory. Therefore, from an engineering point of view, refining only the critical regions is usually the best approach. Now the next question is, where should mesh refinement be applied? Typically, refinement is needed around holes, sharp corners, notches, re-entrant corners, concentrated loads, supports, and locations where different materials meet. These are the regions where stress gradients are highest. Now look at the graph shown below. On the horizontal axis, we have the number of elements, or mesh density. On the vertical axis, we have the calculated quantity, such as stress or displacement. Notice that as the number of elements increases, the numerical solution gradually approaches the exact solution. This phenomenon is known as convergence. Initially, increasing the mesh density improves the accuracy significantly. However, after a certain point, further refinement produces only very small improvements, while increasing computational cost considerably. Therefore, engineers always try to find an optimum mesh, rather than simply creating the finest possible mesh. So remember the key idea written on the poster. Refine the mesh where it is needed, not everywhere. This gives accurate results while keeping the analysis computationally efficient. Now that we know how to improve a mesh, let's understand how individual elements are connected together. Once the mesh has been created, the next step is to define element connectivity. Element connectivity tells the computer which nodes belong to each element. Without proper connectivity, the computer cannot assemble the complete structure correctly. Let's understand this using the two-dimensional example shown here. Notice that the entire structure has been divided into 4 quadrilateral elements named E1, E2, E3, and E4. Each element is connected through a set of numbered nodes. For example, element E1 is connected by nodes 1, 2, 5, and 4. Similarly, the remaining elements are also defined by their corresponding node numbers. This information is stored in a connectivity table. The connectivity table acts like an address book for the finite element model. It tells the software exactly which nodes belong to each element and in what order they are connected. Now look at the one-dimensional example on the right. Here, 3 bar elements are connected using 4 nodes. Element E1 connects nodes 1 and 2. Element E2 connects nodes 2 and 3. Element E3 connects nodes 3 and 4. Notice that adjacent elements share common nodes. This sharing of nodes allows forces and displacements to transfer smoothly from one element to the next. The same principle extends to 3-dimensional elements as well. For example, a tetrahedral element is defined using 4 corner nodes, while a hexahedral element uses 8 corner nodes. Now let's understand why connectivity is so important. During finite element analysis, every element first develops its own local stiffness matrix. However, the structure behaves as one continuous body. Therefore, all these local matrices must be combined into one large global stiffness matrix. Connectivity provides the information required for this assembly process. Without correct connectivity, the global matrix will be assembled incorrectly, and the entire analysis will produce wrong results. To avoid this, engineers follow a few simple rules. Nodes should be numbered systematically. Elements should follow a consistent node ordering, usually counterclockwise for two-dimensional elements. Adjacent elements must share common nodes without duplication or omission. If these rules are followed, the finite element model becomes reliable and accurate. So remember this simple statement. Connectivity is the bridge between individual elements and the complete structure. Now that we know how elements are connected, one more question remains. How does the computer describe the orientation of each individual element? For that, we use coordinate systems. In finite element analysis, every element has its own local coordinate system, while the complete structure is described using a global coordinate system. Let's understand the difference. The global coordinate system is fixed for the entire structure. All nodal coordinates, applied loads, supports, and boundary conditions are defined using this common reference system. No matter how many elements are present, the whole structure shares one global coordinate system. Now consider an individual element. Each element has its own local coordinate system. The local x-axis is usually taken along the length of the element, while the local y-axis is perpendicular to it. Why do we use local coordinates? Because writing the stiffness matrix of an element becomes much simpler when the coordinate system is aligned with the element itself. Now look at the inclined bar shown in the figure. The element is neither horizontal nor vertical. If we directly formulate its equations in the global coordinate system, the mathematics becomes complicated. Instead, we first define a local coordinate system along the element. The element stiffness matrix is derived in these local coordinates. After that, the results are transformed into the global coordinate system using a transformation matrix. Notice the equation shown on the poster. The transformation matrix relates local displacements and forces to their global counterparts. Although the mathematical expressions may appear advanced now, don't worry. In the coming chapters, we will derive these transformation matrices step by step and understand how they are used in finite element formulations. For now, simply remember the purpose. The local coordinate system simplifies the formulation of individual element equations. The global coordinate system combines all elements together, applies boundary conditions, and solves the complete structure. In short, local coordinates are used for element formulation. Global coordinates are used for structural assembly and final solution. Understanding this distinction is essential because every finite element software internally performs these coordinate transformations before solving the global system of equations. In this lecture, we learned why mesh refinement is applied only in critical regions, how element connectivity links all finite elements into one continuous structure, and why both local and global coordinate systems are required in finite element analysis. These concepts prepare us for the final stage of finite element modeling. In the next lecture, we will study boundary conditions, understand the complete FEM modeling workflow, and conclude Chapter 2 with a comprehensive summary of everything we have learned. Thank you for watching. If you found this lecture helpful, please like, share, and subscribe to support the channel. Also, press the bell icon so you don't miss the final part of Chapter 2.